David Josephsen, ladies and gentlemen.
Hey, everybody. Thanks for sticking it out. I'm super excited to be here myself. Anyway, I wanted to talk to you today about what is essentially signal disparity inside of the monitoring systems that we build, and why that signal disparity is a bad thing, how we can avoid it by building monitoring systems that embrace performance data and allow us to alert on what we draw. So since I'll be getting a little philosophical in this talk, I will give you a little bit of background about myself. I've been doing operations work since about the late 90s. I've always been fascinated by monitoring systems, and that fascination eventually turned into hacking on monitoring tools, writing about monitoring tools, and talking about monitoring tools. At this point, I've co-authored or authored 3 books, all of which are about monitoring tools, 2 of which are about Nagios specifically. And now, as the developer evangelist for Librato, my job is basically to hack on, write about, and talk about monitoring tools full-time. So I think a lot about monitoring tools, and I'm old enough, I think, at this point to hopefully have a modicum of perspective. So when I start talking in a few minutes about all of this cliche, buzzword-laden hogwash, including clouds and DevOpsy things and web scale, try not to hold it against me. I need to talk about those things just a little bit, because the systems that we build today in web operations are in fact very different from the systems that we build and maintain in more traditional IT shops. And by fundamentally, I mean that they were built using a different set of requirements to solve a different kind of problem. They're so different, in fact, that in web operations, we very normally have to augment Nagios with other tools in order to effectively monitor them. So let me talk about models for a second. This is a box that I have right now today, OpenBSD box running in a co-location facility in Dallas. It has almost 4 years of uptime. And this used to be, for me, a cause for celebration. And I mean that literally. I had a cron job. It would notify me every time a box hit another year of uptime. We would go and pour one out every single time this happened. So we celebrated it. And I remember this one time I had to move a bunch of racks from one co-location facility to another. And in one of these racks was a host that had over 2,000 days of uptime. So instead of just halting this box, we cross-plugged it into an UPS, threw it into the back of a Nissan 280Z, and rushed with it across town, hoping against hope that this UPS battery would last long enough for us to re-rack the server in time. So these systems, they were the center of my professional life. My servers had names, they had personalities, I knew them, and there was very little that I wouldn't do to keep them running. They were snowflakes, individuals. They each had one job to do, like a process to run, like Apache, QMail, etc. And this was our model. Keep every machine running its process as long as humanly possible. We bought really fancy, expensive hardware with redundant RAM and disk. We put them in restricted access environments. We constructed elaborate organizational defense mechanisms to protect them from change. And when we monitored them, we monitored hosts that were running processes. We were monitoring processes running on hosts. So as long as the hosts were up, as long as they had CPU, disk, and memory enough between them, and as long as the ports that mapped to the services that they ran were available, we were generally happy. We were process-oriented. We were focused on the processes that those hosts were running. Given a finite number of very reliable systems, our problem was to keep the processes running, and we did it very well. A good ops team can keep processes running on hosts in the 99th percentile of uptime until the process becomes irrelevant because, you know, the company went out of business or whatever. This has happened many times to me in the past. I'm good at this job. It's a very different model, however, from the one that I am currently sort of fascinated with and thrown into, which is the services-oriented model that we use in cloud computing. And it's different, really, because cloud computing is awful. When you buy a cloud server, you get this virtual machine instance that you have no control over what hardware has actually been employed, where it's being employed, how it's been employed. You get a thing that looks like a server, but one that you can't invest yourself in. We don't know what kind of BIOS this thing runs. We don't know what kind of network card it has. We have no way of investing ourselves in understanding how to make it reliable. This instance that we've just been handed has to compete for access with physical resources, or to physical resources, with thousands of other machine instances run by thousands of other, cloud computing customers. We are essentially renting access to hardware in a multi-tenancy environment. In fact, AWS is so massive, it's composed of just so many individual disks and DIMMs and RJ45 ports that it's entirely possible that our instance could be running for days on some tiny little bit of malfunctioning hardware, and no one literally will notice. When they do notice, they control the maintenance schedule. So they'll just call you up or email you and say, hey, we're going to go ahead and reboot that MySQL instance for you. And you don't really have any recourse. And these are just the assumptions that are actually built into the model. This is the accepted stuff. On top of that, in real life, it's very difficult to predict what your monthly bill is going to be. There are a confounding array of similarly named services, each with its own UI and management interface. There are absolutely sometimes capacity shortages. And yes, cloud instances in general are just far less stable. Maybe some of you participated along with me in the cloud apocalypse that we had a few years ago. If you haven't, really quickly I'll describe that Amazon AWS is composed of regions. For those of us who don't have government ID cards, there are 3 regions, one on the East Coast and 2 on the West. Each region is composed of multiple availability zones, and each availability zone is a standalone facility. It has its own air conditioning, it has its own power, it has its own everything. So the idea is that you can spread your instances across multiple AZs, and then if AWS has an entire facility size outage, your service will still be fine. But remember that your instances are virtual. They don't actually have hard drives. So what looks like a hard drive inside this thing that looks like a server is actually a web service called EBS, the Elastic Block Store. And it turns out the Elastic Block Store is shared infrastructure. It's a single point of failure across all of the AZs in a region. And so if Amazon has a large blocking problem in EBS, then every region or every zone in the region is affected. And this is basically what happened Cloud Apocalypse Day. I don't know the numbers, but a lot of boxes went down, and a lot of companies went down with them. So that wasn't fun. But outages on this scale in cloud computing are actually an accepted fact of life. We expect them to happen periodically. A few weeks ago, in fact, we had RebootGate, which was caused, excuse me, I'm gonna water myself here. RebootGate was caused by a vulnerability in Zen, which is the hypervisor that is used by both Amazon Web Services and Rackspace. So basically, Amazon woke up one morning and emailed all of its customers saying, hey, we're going to reboot 10% of our cloud instances over the next week, and there's literally nothing anybody can do about it. So if all this sounds horrifying to you, if you're looking at this cloud thing and you're like, why on earth would anyone use this thing, then that's awesome. You're the person that I want to talk to. You are the person for whom this talk was designed. Because it turns out cloud computing requires a different set of design considerations because it's actually a different engineering problem. given an infinite number of unreliable systems, assume that everything below the OS layer is uncontrollable and completely untrustworthy, and build robust services anyway. And you can actually solve this engineering problem, and the companies that solve it correctly stay up. Librato, for example, the company that I currently work for, is wholly instantiated on AWS in US East, and we stayed up through both Cloudpocalypse and RebootGate. Netflix lost 218 Cassandra nodes. That's database tier servers switched off at Amazon's discretion, and their service didn't even blip. So surprisingly, or maybe not surprisingly, I don't know, building infrastructure with the expectation of failure in the underlying layers is a very healthy thing to do. Amazon internally runs a service called Chaos Monkey. You may have heard of it. Chaos Monkey's job is to create random outages inside every subsystem of Netflix's infrastructure. They have open sourced this. You can use it on your infrastructure as well. We have a guy who does that. But so really, if you think about it, Netflix.com runs in a perpetual state of being broken. So pause there and think for a second about how different these models are. The former model is so change averse that engineers willingly participate in meetings with people wearing suits in order that they may convince those men that the changes they want to make to the environment are in fact a good idea. And in the latter, we have a model that is so embracing of change that it literally is trying to destroy itself all the time and failing. So for Netflix and Librato and the companies that are instantiated this way, things like individual host instances no longer matter because they're focused on distributed systems that implement services. This, for example, is what Librato looks like internally. It is composed of a set of interdependent services, each of which runs across many hosts and performs some simple operation on a set of given input. This is our Ultimate service. It's a bad example. Ultimate sort of is an acronym for logs to metrics, but I want you to notice that Ultimate has a name, okay? Each node that runs Ultimate basically listens for log lines that were wrapped in HTTP requests. Ultimate is actually implemented entirely in Go. The hosts don't run Apache or any web server. Ultimate literally runs the HTTP listener inside of itself. When a node gets a request, it unpacks it, parses a metric out of it, tries to inject it into the upstream API. And if everything goes okay, it responds to the client with an HTTP 200. If something goes wrong, it'll pass the appropriate error code back so that the client knows to retry. It has a few dependencies. It requires a data store that it can look up, so it can look up auth information that's embedded in the log lines that we get sent. And once it's parsed the metrics from the log line, obviously it depends on the API to inject metrics further into our system. We generally want to be able to do this. We want to be able to get a metric, parse it, post it into the API, and respond to the client in under 100 milliseconds. So if the 95th percentile latency on any of the services that Ultimate depends on gets near 100 milliseconds, then we're getting into problematic territory and we need to notify someone. So that's an example of a metric that's very important for us. It's one that is external to Ultimate. It's something that Ultimate depends on, but it's also something we want to capture in the context of the Ultimate service. Ultimate is a snowflake. We document every alert that we send from it with a runbook URL like the one you see here. We have to do that because we built it. Like literally no one else understands how Ultimate works. So anytime the engineer on call gets paged about the Ultimate outbox, for example, which is this alert, that page contains a link to this particular runbook, the runbook that you're looking at now. And if you can read it, probably not, it explains basically that yes, there's an outbox queue inside the Ultimate service, and that queue is getting too big, which probably indicates some upstream problem in the API. This is the top half of our Ultimate dashboard, where we actually track the various metrics that are emitted from Ultimate. So these are things like the latency and the queue examples that I just gave. If you squint at it, you'll see we're tracking a whole bunch of really weird-looking, metrics. There is some CPU up there, but there's also things like thread counts, things like the ratio of lines that we parse versus lines that have metrics in them, and et cetera. So every service we build has a name. Every single one of them is a snowflake with its own documentation. Every single one of them has a dashboard just like the one that you just saw for Ultimate. So, and I'll make the point that although the Ultimate system and the services that make it up are all built on the cloud, this model, it's a very common model inside correctly engineered web applications. Every time, even if you're running one of these with on-premises iron, well-built web applications tend to engineer this way. They tend to engineer for reliability in the service layer rather than in the OS or hardware layer. They're very similar to the processes that we used to run in so many ways. They have names, they have personalities, they have documentation. They have one job to do. They tend toward very simple text-based protocols. They depend on other services to perform their job, and it's really important for the people who run them to understand those dependencies and where they lie and how they work and how to measure them. But because they don't trust the underlying hardware or the OS, they literally reside on a different model, so we need to measure them differently. We want to know about things like latency and queues and workers and all of the stuff that I've been talking about all day long, rather than things like disks and CPU and memory. To measure these things, I generally need to be inside the process space of the thing that I want to measure. So I need to be inside Ultimate to measure Ultimate, which means when I'm building Ultimate, whoever's building it needs to instrument it. And because the services I'm building run across a whole bunch of machines, I very often want to aggregate and summarize the data that comes out of this service, at the service level rather than at the host level. I want a single number. I want to know how many messages are in Ultimate's outbox queue. I don't want to know how many messages are in each Ultimate node's outbox queue. So this last bullet point is really the focus of this entire ramble. So I finally gotten to the point, 17 minutes, just so you know. Not only do I need to know these sort of like service level single digit measurements, I also need to be able to alert on them. And that's tricky, and it's easy to get wrong. We only have, we have two very different sets of requirements here for two very different sets of engineering, systems engineering. Nagios is well suited for the first type, but it's not especially well suited for the second. And so when you realize how different these are, when you have the realization that, wow, this really is a completely different world, it's very natural to want to draw a line between these models, to build a wall between them, to say, these two models are mutually exclusive, and on this side of the wall, we run Nagios, and therefore, monitoring web applications or applications that are services-oriented is someone else's job. And I'm here standing up before you because I think that's a very dangerous sort of cognitive leap to make. When you make it, when you build that wall, what you end up with is disparate telemetry signals in the same organization. This is extremely unhealthy. These represent multiple tools with different views of reality, and therefore they represent different views of reality inside two different engineering organizations. And I'm here to tell you that those two signals will never align. If you want to argue about it in the hallway, I'd be happy to argue. I personally feel that it's actually an impossible problem to make telemetry signals from two different monitoring systems align with each other in every case. I've tried very hard to do it, and I've failed. Well, people better than me have tried too. So I advise you to avoid this. I'm here today begging you to avoid this. I think that when you do this, you invite alerts that don't match your telemetry data, so that when I get paged in the middle of the night for something that Nagios says is broken, and I look at my data and my data does not correlate with that alert, it undermines the credibility of both systems. I feel very strongly that if you do this enough times, everyone, or at least the people, everyone but the new guy, will ignore both of these systems eventually, because they don't know which one to trust, and so they wind up trusting neither. It doesn't matter if one is actually more accurate than the other or not. Secondly, the wall that you build between these models silos operational knowledge behind organizational structure. It means that everyone knows less, in a way. And worse, it means that different engineers are making design and engineering decisions based on different data. And they literally, usually, don't know about the other data. And third, it's just a duplication of effort. I could, for example, save Nagios all of the computational burden of check ICMP if I could set up a passive equivalent that used metric data, because I can assume that if a host is emitting metric data, that it's up. So anytime there's a functional overlap between these two signals, I'm wasting bandwidth, I'm wasting computational resources, I'm wasting money, I'm wasting man-hours. So I strongly believe that whatever team currently owns monitoring needs to embrace both models. I think if you can't embrace both models, you should get out of the way and let some other team own monitoring. I think it's a very important organizational decision that everyone needs to make. Ideally, there should exist a common stream of metrics that everyone can emit performance and state data to. And then we can point pollers like Nagios or any sort of individual state or event processor at the common stream of data. I'm not saying that this is in exclusion to allowing Nagios to poll hosts and services directly. This is in addition to the direct polling that you want to do. We can also point Nagios at a common telemetry stream when it makes sense to do so. When we do this, it unifies the models and it creates a single source of truth for monitoring data that everyone can consume. It basically ensures that we don't have a disparity of signals because we're literally alerting on what we draw. So the question becomes, what is this thing? And I think in the near future, many of us will be using Heka or Riemann as a top-level telemetry processing system. Heka, as I stand here today, can emit passive service checks into Nagios, and I'm very excited about it. But alas, I am not set up to demo it for you today. I do want to show you a few of these tools, though, and I want to give you a feel for how to get them working together and kind of how hard that is. So the first thing I want to show you is how to set up Nagios to emit performance data to both Graphite and Librato simultaneously. So basically what we're going to do is we're going to take Nagios, we're going to put a metrics collection and processing middleware on it, and that middleware is going to emit to multiple upstream metrics systems simultaneously. And then, once we've done that, we'll take Graphite and we will use Graphite as if it were a top-level telemetry stream, and we'll configure Nagios to pull it for some data that comes out of collectD. So we're going to use a different agent. You guys familiar with collectD? It's basically a standalone agent. It's going to emit metrics up to Graphite, and then we're going to tell Nagios, hey Nagios, go look at Graphite and tell me what the server load is on a server that you're not actually monitoring. And Nagios can do this because collectD is emitting load information up to Graphite. So I had planned to do this as a live demo, but I was eating lunch today, and I was thinking about Ethan's keynote with his screen scrape slides that were going on behind him. And I thought, instead of awkwardly live demoing this, it might be less painful if I made a scrape movie and then sort of awkwardly tried to narrate it. So this movie is 3 hours old. We'll see how it goes, I suppose. Pretty sure I know where the pause button is, too. So Pretty much everything that you're about to see is running on this laptop. This screen scrape was made on those tables out there. I have a Nagios instance. It's monitoring several vagrant hosts that are also running on this laptop. I also have an empty graphite, and I have 2 terminals up that are pointing, one at graphite on the right, Nagios on the left. So I'm going to start out by making a brand new Librato account. Go ahead, self. There you go. We'll go to just metrics.librato.com. We'll pick the yellow try me button. We'll make up a bogus email address, which totally works, by the way. You can do that. Librato will take me helpfully to its, I see you don't have any metrics. Would you like some help with that screen? And at the bottom of that screen, you'll find our API token. So this big random blob down here is basically auth information. This is what I would use in my client when I want to send stuff to Librato. It's how Librato will know who I am later. So having done that, I will go to the shell and I'll install. This is the nice part, by the way, about making this a screen scrape. So like I can zoom in on stuff and you guys can actually see what I'm typing, which is cool. I thought it was cool anyway. I will install Graphios, which is available from GitHub. Probably in the next couple days, you should be able to just pip install Graphios, and that'll just work. But that was pretty much the install. Boom, it just installed. And we're going into the Graphios config right now to enable Carbon. First, I will enable Carbon by setting enable Carbon to true. So there you go, enable Carbon true. And then we will point it at my local vagrant Graphios, or my local vagrant graphite instance, which is named graphite. Then I'll scroll down to the Librato section. I'll enable Librato by setting it to true. I'll give it the bogus email and API key. Uncomment them, obviously. And I do want to point out this oh my god super important setting that will save you money. Librato does charge you for what you store if you ever come off the development plan, which most of you never do. So you kind of want to be careful about what you emit. So that's a whitelist, basically, that says, hey, here are a bunch of regular expressions that match things that I want to send to Librato, like RTA and load and et cetera. So having done that, I should take a second to show you the Nagios config, because what actually happened in the background there when the pip install kicked off was the setup py inside Graphios. Oh, sorry, I'm going to start the Graphios process. There are actually 2 init scripts inside Etsy, so you don't have to run it like this. You can just copy the init script over based on Debian or Red Hat and service start it or whatever. But anyway, the install added the requisite configuration, performance data configuration to the Nagios config. So I'm showing you that now. It'll be pasted down there at the bottom of the file so that you can delete it very simply. Basically, we've enabled performance data. We've configured performance data to, emit to a log file that Graphios knows how to parse. If it's actually pretty smart if it exists, if you have already this configuration inside your Nagios CFG, it'll still add it, but it'll all be commented out there at the bottom. So it's not destructive, very destructive, et cetera. So that being the case, we can restart Nagios, and then we ought to be able to go into our graphics, or our graphing solutions and see, there we go, Otokami is the name of my laptop. So Otokami Nagios is basically a prefix. So everything that Nagios via Graphios sends into one of these graphing programs is going to be prefixed with that. You see we have metrics from 4 different boxes all running on the laptop. I'm going to choose ping RTA, so this is output from check ICMP to graph. So I think it's not showing up because time stuff is too long. So I'm going to change hours to minutes. And then you'll see data appear over on the right-hand side of the screen. Super exciting. Always super exciting to see data. Then we can go into Librato, put away the can we help you screen and click metrics, and you'll see that the metrics in Librato have also populated. Our prefix, ping RTA, and Librato basically uses source as a different dimension. Oh, and we're also going to do Grafana. If you guys haven't seen Grafana, super exciting project. It is a replacement UI for pretty much all of these sort of back-end, graphics and visualization systems. Feeling super eloquent today. Grafana has a really nice interface for sort of choosing metrics. It allows you to sort of build metric paths from left to right. And then we sort of scraped across the data to. So that is what we just did. We basically created 2 external telemetry streams with Nagios in the middle, Nagios basically emitting to both. And now, for my next trick, we're going to get collectD pointed at graphite, and then we'll add a Nagios check to pull graphite for state data from collectD. So many names. So many names, so many tools. Oh. See, I bought the $40 clicker. Pro tip. The $40 clicker has this button that's like end the presentation right underneath the button for next slide. So, like if I were you, I would buy like the $60 clicker. Let's see, there we go. Okay, me. So we're gonna go over to the Nagios box and shell. The first thing we're going to do is make sure that collectD is running. collectD is a super easy installation, and this is a Nagios conference, so I wasn't really gonna bore you with how to install collectD. It's apt-get install collectD, and it's running. I will show you the relevant section of the configuration file where I tell collectD, hey, go send your stuff to Graphite. It's pretty much trivial. I just uncomment one line that's like, enable the Graphite write plugin, and then, yeah, it's basically what you would expect, I think. It's the name of the Graphite server, et cetera. And then poof, over here we have a new heading underneath Graphite. I'll collapse the Nagios stuff, and there you have a collectD section that has all the same hosts listed. And here we have load. So the goal here is we want Nagios basically to be able to alert us when the short-term load of this box goes above whatever threshold. I think I used like 5 and 10 for warning and critical. In order to do this with Nagios, we would generally have to install like a check NCSA, check SSH, check NRPE, check whatever, to remotely call over to another system and then execute, check load, whatever on that system, and then pull the request back across to Nagios. Or we'd have to use something like an MK, that would just do that automatically for us on the remote host and then passively push the requests apart. So what we're doing here is we already have collectD on this system. So we're assuming we already have a thingy over there that's giving us the piece of information that we need. I'm using load as the example, but it doesn't have to be load. This could literally be any sort of agent or instrumentation library or any sort of bit of data that we already have that we're already collecting by some other means. I'm pushing it up into Graphite. It's already in Graphite. It's right there. It's the short-term load thing. Yeah, there you go. The laser works all right. And now we're basically just going to, now we're going to go to the other slide because that was fun. Does anyone know the fast forward button in Keynote? Well, we didn't get very far. I really don't know how to fast forward that. If I move my mouse over there, can I? No. Huh. Well, I promise it's working. Here, let's do these. Here's the cute little video I made. Let's pull that across. I actually shut down the Vagrant boxes because I didn't want them crashing or otherwise causing me grief up here. We could take a look at all of this if they were still running. That's pretty much where we were. Okay, so down to load, showing you that load is there, showing you that short term is there. It's coming out of collectD, not Nagios. We'll go over to Grafana and look at the same thing because Grafana is super pretty. Who wouldn't want to see graph in Grafana? Grafana is also nice because it actually includes wildcards. So if you can see in here, see that top item in the pull-down metric is, or option in the pull-down is asterisk. I just chose it there. So literally I just said to Grafana, hey, I want collect D, every host, load, select metric, and then I'm short-terming it. So it draws like both hosts that I'm collecting it from there, which is nice. So now we are going to take a look at the Nagios services configuration where that command is set up. And I have it commented down at the bottom. Yeah, I was cheating, whatever. I mean, you didn't really want to like sit through me typing it all out, so. Also, yeah, there's a bug in there. I'm aware that it actually does say check load in the check command. It should say check graphite. I didn't have time to fix it. I'll also show you what the actual command looks like. Full screen that. So there's the command definition, check graphite. Basically, it's a Ruby script. It goes out there, you point it at your graphite server, you tell it what metric you want, you tell it critical and warning thresholds. It'll go out there, it'll pull like last 5 measurements, it'll average them together, and it'll give you back Nagios active check, returns. So having enabled that, I'm restarting Nagios probably, making sure it's running. And then we'll go back out to Nagios and take a look, and sure enough, there's a graphite load command right there. So that has output from graphite. So it's like, okay, value 0, 0. We're good to go. So thank you, video. So again, just for what it's worth, this is what we've configured. We have a foreign monitoring tool, which might have been a log sync or an instrumentation library. We've stored a metric from it into a common access telemetry system. We've configured Nagios to pull it for data, thereby saving ourselves from setting up a NRPE check over the wire. And that's pretty much alerting on what you draw in a nutshell. Like I said, I made this video pretty much on this laptop, so if you want to play with any of this stuff or see it or get a more in-depth demo, I'd be happy to sit down and run through some of this and actually, dig into it. And at this point, I will welcome questions, comments, and points of clarification.
Yeah, I'm just wondering if collect D caches metrics locally. So if it were to lose connection to graphite temporarily, kind of like how Graphios works, it would, once the connection's reestablished, it would send all the metrics up to graphite?
I think the question was if I lose network connectivity between CollectD and graphite, will I still get metrics traffic?
Once the connection's reestablished, would it?
Yeah, it depends kind of on your configuration. There are a lot of CollectD plugins out there. There is caching plugin. There is also a network plugin that you can do like, send your CollectDs to one CollectD and then roll them up from there. So there's stuff you can build there depending on how much you care, yeah. By default, I think you probably just drop metrics on the floor.
Now from the beginning, I'm curious, did the server on the UPS survive the trip?
Sorry. Yes, the question was, did the server on the UPS survive the trip? And absolutely, we made it with, I think, minutes to spare. And I'm trying to think of whatever happened to that server. It was an FTP system, as I recall. It must have gone down at some point, but I don't know when. Sorry.
A lot of the server level metrics depend upon developers, including counter emitting code inside their tools, inside their processes. Did you have any problems getting them to embrace that methodology, or any carrot or stick you used?
One more time, I'm sorry, just the first part?
Yeah, a lot of when you're emitting stuff to capture regarding services, requires the developers to include code that emits the counter metrics. Did you have any difficulty getting them to alter the code base to allow that?
So yeah, So the question basically is, did I have to fight developers to get them started actually emitting metrics into a common metrics repository? So I've only recently really started working with, programmers in earnest. But in my sort of somewhat limited experience so far, they're usually already doing something. Whether it's a software as a service that they're using in secret, or some machine that they've managed to get on the network that they're repurposing. Developers, in my experience, generally want to know what's going on inside the things that they're building, if they're the right kind of developers. I'm sure that's probably not universally true. In terms of sticks, or carrots. You said carrot and I said stick, that's funny. Punish them! Ah! In terms of carrots, beyond having the data there and them seeing the data and actually understanding and having it solve a problem for them, I'm not sure how else they could be convinced. It would also sort of depend on how black box of a stack they're in. I would think that some of them would probably be more apt than others. Not much of an answer, sorry.
We have any other questions? Well, if that's going to do it, then that's going to do it for the afternoon. We survived day 3. Thank you, everybody. Nice round of applause for David Josephsen.
You guys.